Now we're going to look at logarithmic functions and their graphs. So that begs the first question, well, what is a logarithm? Define a logarithm as, say, y equals log base a of x if and only if x equals a to the y power. In the simplest terms, a logarithm is an exponent. So what I often like to write is that if we start with something we know, if I have a base raised to an exponent, that'll give me some answer. And if that's the case, what that means is that the exponent equals log base, whatever the base is, of the answer. And that's sort of how you switch things around, and that's exactly what this is saying here in just more typical terms that we'll see. And what this does is this gives us our function, f of x equals log base a of x. And that is a logarithmic function with base a. A can be almost any number larger than 0, of course, and not 1. However, we'll typically see the bases are 10 or e. Some of the basic characteristics or properties of logarithms are as follows. If log base a of 1 equals 0, well, that's true because a to the 0 power equals 1. Log base a of a equals 1, well, because a to the first equals a. Log base a of a to the x equals x, and a to the log base a of x equals x. And that's because they're the inverses. That's the inverse property here. Finally, if log base a of x equals log base a of y, then we know that x must equal y. And that is the one-to-one property. X must equal y if everything else is the same. Now let's look at the graph of the logarithmic function. The first thing to note is that it is the inverse of the function y equals a to the x, which we have here that we learned about before, the exponential function. And an inverse function, as you recall, to find it, you switch x and y and solve for the new y. So in terms of points, you're switching x and y, which gives us a reflection along the line y equals x. So for example, we knew that we had an intercept of 0, 1 with the exponential function, which means we'll have now as the y-intercept, and we'll now have an x-intercept reversing x's and y's of 1, 0 for the logarithmic function. Another thing to point is look at the domain and range, and here's the general shape, of course, of the function. So let's look at the domain, range, zeros, intercepts, and asymptote. First of all, the domain of the logarithmic function is going to be 0 to infinity. So that looks like from 0 all the way to infinity we're going to have values. So again, which is the range of the exponential function. So the range of the logarithmic function is the domain of the exponential function. So the range is going to be all real numbers, or negative infinity to infinity. The zeros, I do have zeros at this point, and that's going to be 1, 0. And the y-intercept, well, we don't have any. There is no y-intercept for the logarithmic function. Never, x never equals 0. X cannot equal 0. So it also gives me an asymptote then of x equals 0. I have a vertical asymptote. And here we have the natural logarithmic function. So the natural logarithmic function is denoted by ln, or for the natural log. Ln of x, if and only if x is e to the y. So this is basically saying the log base e is written as ln, the natural log. And this one comes up a lot, and this is one of the most common bases that we're going to use. And in terms of the graph, what it looks like, well, it looks just like other ones. There's the shape, there's the parent function. Another thing to point is it does have that intercept of 1, 0. And that is f of x equals natural log of x.